Hold on. Alrighty. Full screen. Wow, almost full house today. 38 now. Very good. $39. Okay, can you see the slides? Nampak? All right, let's move on to carrier transport phenomena. Okay, as usual, before we continue, let's recap on the contents that we've learned last time. Right, so we've covered this one briefly and partly here and there last time during the lecture. So let's recap again. Define intrinsic semiconductor. Easiest one. What's the most important keyword to replace intrinsic? Undoped, pure. Okay, so those are the words. Pure, right? Good. So what's the source of electrons and holes in intrinsic semiconductor? Where do you get free electrons and free holes in intrinsic silicon, for example? How do you get it? Anyone? How do you get them to be free and available for conduction? Faris knows. Okay, Faris, let's share your answers. Thermal excitation, okay? So what we've covered so far is thermal excitation, right? So you can revisit the YouTube video on the conductivity of your silicon wafer to light up LED. I think I forwarded last 2 weeks or so, if I'm not mistaken. When you supply the heat to the system, to the silicon, you can see improved electrical conductivity, which is due to thermal excitation of electrons, right? So we're going to learn about light later on. Faris said thermal excitation light. We're going to learn about how to induce formation of new carriers or excess carriers, I believe, in the next topic, okay, after this carrier transport phenomena, where you're going to have like a couple of methods that you can use in order to generate excess carriers or new carriers after your semiconductor has reached equilibrium condition. Right, extrinsic semiconductor is very straightforward. It's just the opposite of intrinsic, where you dope your semiconductor with p-type or n-type dopants in order to produce more holes or more electrons. All right. So in that particular condition, you are not going to have n equals to p anymore, as what you have in intrinsic semiconductor. But on the other hand, you're going to have more of holes or more of electrons, which are going to be dominant in your semiconductor. Right, the last one. You are given, it's not n there, it's a p-type, a p-type. If n-type, then n-type. Okay, you are given a p-type silicon wafer that is extrinsic. How do you turn it to be intrinsic? Right, so how do you turn the extrinsic silicon to be intrinsic silicon? Give me 2 ways to do it. How? Anyone? How about Arisha? Arisha Shazwin. Saya nak panggil nama, saya tak pernah panggil, jarang kedengaran. Let me call your name. Arisha, you can unmute yourself. You can also write it down there in the chat box. Come on. before we go to lunch? Yeah, yes, okay. So how do you convert extrinsic silicon to intrinsic silicon? Oh, berbalik dari tandas pula. Right, siapa yang belum balik dari tandas? Siapa belum balik lah, siapa yang tak pergi tandas lah. Dayang Hamizah. Dayang or Hamizah? Come on. How do you convert extrinsic? Okay, dope. Can you elaborate? So now you've got a p-type dope wafer. So how do you then turn it to be intrinsic? Yeah, you said dope. Okay, how? Elaborate a little bit. Boleh unmute yourself. Go ahead. How do you do that exactly? Can write down or can I unmute yourself? Any helper here? Let me see. So many Nur here. How about Sari Izyani? Sari Izyani. How do we do that? How do we do that? Dayang, you've got your full elaboration already? Anyone? Kita dah discuss kan? Last class, 2 ways to do that. 2 ways. There. Freeze out method. Freeze out. Are you gonna go for freeze out? Freeze out means you're gonna reduce the temperature, right? Then you're not gonna. So let me see. Arisha said, naikkan temperature. Okay. Until. Naikkan temperature is a way to do it, but until, what's the threshold? Can you just get it at any temperature? What is the condition that needs to be fulfilled? Which region are we talking about here? If you're talking about the graph last time, the electron density on the y and temperature on the x, which region are you talking here? Freeze out or extrinsic or the third region? The leftmost, center, or the right one? For increasing temperature, so the intrinsic carrier, intrinsic concentration increases. Yes, okay. So we are talking about which region here? First region on the left, second region in the center, or third region on the right? So this question is talking about which region? Center ke? Third region, right? Yes, Nurahan, third region. So where you have, remember the first region is you have the freeze out, you have a gradient, right? A positive gradient, and then the central region will be the extrinsic region, okay? Where you start to ionize the dopants in the lattice in order to make sure that the density of N or density of P is equal to ND or NA as intended, right? Where you achieve 100% ionization. And beyond that, beyond the central region, when you start to see the positive gradient again, the third region, where it turns to be intrinsic, okay? It turns to be intrinsic again. So that is one. Increasing the temperature is the first answer. How about the second answer? Just now, sampai cakap, Dayang got it right. Dope, but how? Dope is very broad. So how do you explain dope? How do you get intrinsic from doping? Because you already have your p-type dopant, right? In the lattice, dope with group 15 element, compensate, right? We call it compensated semiconductor, right? So you need to introduce opposite dopant atoms into the lattice. Doping is right, but Generally, when we talk about doping, you're talking about increasing conductivity. That means going further up. So if you're talking about 10 to the 14, then we're talking about increasing it to 10, 15, or 16, or 17, or 19, or so. But this one is compensated doping. You have to reverse. You have to introduce opposite polarity into the lattice in order to achieve compensated semiconductor. So at that point where your ND is equal to NA, or NA equal to ND, at that point you're going to have no majority carriers anymore, and your semiconductor is going to be called compensated semiconductor, and it's now intrinsic again, right? Intrinsic again. So two methods: increasing temperature and compensated doping. Right, clear. So let's move on to our next topic, which is on carrier transport phenomena. So we have discussed about electrons and holes, majority carriers, minority carriers, law of mass action, and stuff like that. Now we're going to look at how do they move in our semiconductor. How do the carriers move? Okay. So we're going to look into introduction to charge transport. We're going to look into drift as the first method, as the first movement, motion, if you like, or carrier transport mode. The first one would be drift. The second one would be diffusion. And we're also going to look into Hall effect, which is a method to characterize the carrier transport in our semiconductor material. So when we talk about charge transport, the movement of it refers to the movement of charge carriers around the semiconductor. So how do the carriers move in our semiconductor material? Okay, drift is the first one. Drift is the movement of electrical charges due to presence of electric field, right? So drift is the first one, movement of electrical charges due to presence of electric field. So that means if you want to have drift component in your semiconductor, you need to introduce electric field into the system. So there need to be electric field in the semiconductor, right? On the other hand, the second one is called diffusion, movement of electrical charges due to presence of concentration gradient. Okay, movement of electrical charges due to presence of concentration gradient. So we're going to look into this a little bit later. So consider free charge carriers moving in a semiconductor due to thermal energy. So by default, if you have a semiconductor material at some temperature, so the electrical charges or the carriers are always going to be associated with thermal energy from the lattice. Okay, all the free carriers move with an average velocity called thermal velocity. So this is the default condition. Your carriers are going to move with an average velocity called thermal velocity, and at room temperature, so the value of your thermal velocity will be somewhere around 10 to the 7 centimeter per second. And if you convert this into kilometer per hour, you're going to get 360,000 km per hour. Okay. So kalau you pernah drive kereta, you pernah drive sampai tahap ni ke? 360,000 km per hour. It's not even on the meter, right? Meter berapa? 180, 200 maybe, 200 plus km per hour. So this is like 360,000 km per hour. So the movement of the carriers are scattered by the host lattice. So dia akan bergerak randomly. So it's going to be random movement of the charge carriers. So they're gonna experience scattering by the lattice. Dia macam berlanggar with each other, berlanggar with the lattice. And also by dopant atoms that have been incorporated into the lattice in order to alter the conductivity. And also scattering by other impurities that are present in the lattice as well. So collision with the lattice, collision with the dopant atoms, collision with other impurities if they are present in the lattice. If there's no electric field and no concentration gradient, the direction of the thermal velocity after each scattering event is random. So it's going to be shown here. I'm gonna show you a website later on. So tengok kat sini, on the right hand side, the movement of the carriers are random in nature. So pelanggaran tu just random, dia langgar, patah balik, langgar dopant, langgar lattice. each other, right? So it's going to be random. Thus, the net velocity of all the free carriers combined is 0. So the net velocity is 0, no net transport of charge. So there's no net transport, which means that there's no specific direction of movement. Okay, tak ada specific direction of motion of the free carriers because of random scattering. So what we can see is only random movement, and that's it. There's no net movement in certain direction. So the path of the carrier is characterized by mean free time between subsequent scattering events. So the time between the next scattering event, before the next collision. So from this collision to the next collision, the time they have is called mean free time between collision. Okay, so that's what characterizes the path of the carrier in this particular case. On the other hand, okay, before we go to the video, drift is the movement of electrical charges due to presence of electric field. If there is an electric field, there will be a net motion of the carriers. If you compare with the previous case where there's no electric field, so the movement is characterized by the net scattering, okay, by the net scattering, which doesn't have any net motion into any specific direction. But with drift, it's gonna be a net motion into a specific direction depending on the charges, right? So a free electron moving in an electric field has a net velocity in a direction opposite to the direction of electric field. And on the other hand, for holes, they are following the direction of electric field. So let me show you one example, one website that you can always refer to from now onwards. A very good one. Let me share on the screen. Up, sorry. Okay, share. What's the thing? I think this one. Okay, can you see the website now? Tambah? Okay, good. This is called, you can always refer to this later on. You can search PV CD-ROM. And you can just go search PV CD-ROM here. You Google search PV CD-ROM, nanti dia akan naik website ni. So it's a very good website for your reference. So it's meant for solar cell. It's meant for solar cell, semiconductor physics, device physics, cell fabrication, and everything. So kalau you tengok kat content ni on the left, you can see introduction, properties of sunlight, semiconductor and junction. If I can open this up, you can see semiconductor structure, conductivity, band gap, all the stuff that you have learned before, and most of the stuff that we're going to learn after this. Generation, recombination, blah, 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 blah. PN junction, diode properties, sampailah ke operation of solar cell. So, solar cell, and how do we manufacture solar cell in the industry, and then characterizations involved. So those of you who are working on solar cell related projects for your FYP, for example, then this is a very good reference website for you to look at. Okay, walaupun you tak buat research related to solar cell, the basics or the fundamentals, the semiconductor physics used in solar cells are actually the very same basics that we're going to learn in this course, because the basics or the fundamentals are shared for a range of different semiconductor devices. Cuma dekat device level je is different, right? The operation is different. But when it comes to the band gap, doping, thermal equilibrium, all those stuff, excitation, they're all the same thing. Cumanya when we discuss later on MOSFET and LED, detectors, solar cell, lasers, then they're going to split into different device operation and their own unique properties. But the basics are still the same for all. So you can come to this and look at drift, for example. Animation. I'm just going to show you the animation that you can learn from here, because the things that I put on the note is static, gambar je, just pictures. So if you look at this animation, you understand more. So I can just play here, start. So if there is no electric field, this is what you're going to see. Just like what we discussed on our previous slide. Okay, there's no net motion. On the other hand, if you click this next, you're going to see net motion with electric field. Okay, so dekat atas ada electric field, it's going to be random. There's no net direction at all. On the other hand, you can still see a bit of scattering in the electric field region dekat bawah ni, but then the net motion is still in one direction. Walaupun dia scattered quite randomly, but eventually it moves into one direction. Okay, in comparison to the first one. Let's look at it again. Okay, let's look at the no electric field case. So it's just random hitting each other and lattice, dopant, impurities, and there's no net movement at all. If you go here, you're going to see a net motion. However, there are still scattering events involved. Okay, so eventually it's moving to one direction. So this is very good in order to illustrate the thing that we want to learn. So for example, if you can go down here, you can also learn about this. Press start. Tengok itu, the red one is electron, the blue one is hole. Okay, just for us to illustrate. And then you can see that if there is no electric field, the case yang kat atas dia macam just, there's no net movement lah, dia akan just moving about the same position more or less. On the other hand, kalau tengok yang kat bawah tu, okay, let me restart. Okay, you can look at that. So the hole is moving into one direction, into the electric field direction on the left, and then on the other hand, the electron is moving into the opposite direction. Okay, this principle is important. Sekarang you may not see yet. We're going to see later on in our device when we talk about p-n junction. When you want to generate electron hole pairs, and you want them to be separated from each other, so you need to use electric field in order to separate hole into one direction, electron in one direction, so that each of them can be collected separately at the electrodes. Okay, so we're going to see later on in solar cell and some other p-n junction based devices that you need to separate the carriers into their respective direction. If you're not able to do that, then they will recombine. They akan bergabung dan annihilate each other, and they're going to be lost. Okay, they're going to be lost. So you can always come here and try for yourself. So this one is without electric field, electron and holes move around randomly. Turn the electric field on to watch electron and holes drifting. Drifting means in electric field. Okay, without electric field, there will not be any drift component at all. So now it's random in nature, blue and red. Now let's turn on the field. Sekarang boleh nampak kan, the movement is in one direction for electrons and another direction for hole, right? So it's going to be separated. So this is what drives carrier separation in our device later on. Okay, kita akan tengok later on. So this is very fundamental. Now you can see clearer in comparison to the nodes. So nodes just gambar ya. So you cannot see the movement. So you can come here and see later on the p-n junction, for example. You can always come here again to see the principle of the junction. Nantilah kita akan come back to this when we go into the p-n junction topic. Okay, p-n junction thing is here. So let me go back to the nodes. So all you have to do is search a PV CD-ROM, then you'll be right there. Okay, let's go back to the slides. Okay, nampak slide kan? Just to confirm before I continue. Okay ya, nampak kan? Yep, okay, good. So that's drift. So you have seen drift, and you have seen the movement of carriers without electric field as well. So you can now differentiate the movement. Okay, you can now see the effects of electric field in a semiconductor material. So ni yang tadi so these are the underlying principles that governs the movement just now. Okay, you can come here and see. Okay, drift. I can just imagine. Okay, consider electrons, because we're going to come to the what we call mobility and the current density related to drift. Okay, mobility and current density related to drift, and it's going to be given by, and J here is current density. J is the current density. So if you look down here, let me write down. So the net motion, due to the net motion, you need to use this equation in order to calculate, and that will be given by this. So when you have a drift component present in your semiconductor, so due to the movement of your carriers, current density is going to be produced from each carrier. So you're going to have current density associated with hole and also current density associated with electron. Okay, so and the current density due to the drift component is given by J equals to a negative Q n. Q is the electron charge, n is the electron density, mu is the mobility of electron, mu is the mobility of electron, and E is the electric field. The electric field supplied to the system in order to induce the drift. Okay, so these can also be summarized as this. The equation above can also be summarized as this, where this conductivity component belongs to this. Okay, NQ mu will give you the conductivity component. Okay, electric field itu sama aja. Okay, you can then manipulate the equation to calculate mobility and whatever is asked. So the bottom line is here you have to know this. NQ mu will give you the conductivity or reciprocal of resistivity, because in some questions conductivity is not given, sorry, but instead you have to calculate the conductivity from the inverse of resistivity. So what is mobility? It's a material parameter that depends on the semiconductor itself. That is doping densities and temperature. More or less, it's about movement of the carriers. Okay, movement of the carriers. So this mobility mu. So we're gonna have either mu E or mu H. E is for electron and H is for hole. So they are dependent on several parameters. For example, the doping density of the semiconductor material. So you can look at this graph. Here, mobility is given on the y-axis. Either it's for N and P, E and H, okay? So you boleh guna, some cases you will see this as mu N, mu H. No, mu P, N, P, sorry, P. So either you put E or N sama aja, or H or P sama aja. So you are referring to the same thing. So the top curve is for electron and the bottom curve is for hole. So what do we see here? What happens when the doping density increases? What happens to the mobility? What do you see here on the graph? What happens when the doping density increases? What happens to the mobility? Decrease, right? So you can see that when you increase the doping density to say around early 1016, so you won't be able to see a significant reduction yet. However, it's reducing, but the gradient is not that steep, right? It's rather a flat curve, but gradually going down. However, when you go beyond 1016, you can start to see a more significant effect of the doping density to the mobility of electrons and holes. So both are going to reduce. For example, if you talk about electrons, then if you dope your silicon, for example, at 10 to the 14, your mobility is somewhere around 1358 cm squared per volt second. Okay. On the other hand, if you increase your doping density to 10 to the 17, if you increase from here to there, So your mobility is going to be dropped down to 800 centimeters squared per volt second for electrons. Okay, so the same goes to the hole as well. So it drops from 461 to 331. So if you dope your silicon beyond 17, you can also get the same trend pretty much for gallium arsenide and germanium, but the rate is different depending on the material. And for this particular chart is for silicon at 300 Kelvin. Okay. Right, let's go. What time is it? All right. Dependence on doping and temperature. Okay, tengok kat sini. Mu is on the y-axis. Right, mu is on the y-axis, and temperature is on the x-axis. So the graph shows electron mobility in silicon versus temperature for various donor concentration. Various donor concentration. So this one is P-type silicon or N-type silicon. For various donor concentration. N-type or P-type? P-type ke, Juwaria? N-type, right? ND, remember? Donor. Donor, ND. Donate. Donate 1 electron. So how could it donate 1 electron? Because it has 1 extra electron, right? So it must come from group 5 or group 15, like phosphorus, arsenic, antimony. So therefore it's an N-type silicon. N-type. Okay. So now let's look at the mobility against doping concentration. So we have learned that in our previous slide, when you increase the dopant density or doping level, for example, the mobility reduces. Okay, the mobility reduces. So now, when you increase the doping level from 1015 up here to 1019 down here, we also see that the mobility reduces, right? Betul? Can you see that? Betul? Sama dengan this arrow here is the same as this arrow here, right? Cuma plotted differently lah, but it's telling you the same thing, right? So increased doping level results in lower mobility. So same, increased doping level to the bottom part of the graph leads to reduced mobility. Okay, so why is it so? Why do you think increased doping level results in lower carrier mobility? What is carrier mobility? Carrier mobility is how easy for the carriers to move. Kalau you duduk, kalau let's say if you have a room to rent out, okay, you ada satu bilik if you want to rent with your friends, for example, you have one room, one small room, then only two fellows going in, and you and your roommate, for example. Is it easy to move in the room? Susah nak gerak ke? You ada one master bedroom, for example, and there's only 2 of you. Is it easy to move? Will you collide with each other all the time? Difficult to move. Sakina sangat difficult to move. Susah ke? You ada master bedroom tau. Okay lah, relatively easy, right? Okay. Compared to if you have the same room, but you have like 20 people going in. You ada same room, master bedroom sama size, but then you have like 20 people going into the room at the same time. Is it easy to move? More difficult, right? So sama, dia punya principle sama macam the doping thing, okay? So you ada space yang sama untuk you masuk dalam lattice. Then case number 1, you're gonna dope the silicon to 10 to the 14. Maksudnya it's not that crowded, right? Compared to if you dope to 10 to the 19, lagi banyak impurity. You put more and more impurity atoms into the lattice in order to improve conductivity. So as a result, it's more crowded in the space. So that makes it more difficult to move around. Okay. So sama principle dia macam mobility, right? So if you dope to higher level, then it's more difficult to move, and then the mobility will drop. Mobility of the carriers will drop. So that's why your mobility here drops when your doping level increases. Okay. So we're going to see later on which one dominate, what dominates at which level. Yeah, we're going to come to this later on. Just KIV first. So for lightly doped samples, say 10 to the 14, lattice scattering dominates. So when you have lightly doped, so the lattice scattering that we discussed in our slides before the electric field, lattice scattering dominates. Okay, at some temperature. So your carrier movement will be determined by the lattice scattering at that particular point. So mobility decreases as the temperature increases. Kenapa mobility decreases as temperature increases? What happens if you increase the temperature of your silicon? Apa jadi dekat lattice? Oh, vibrate ke? Haziq? Right, so as a result, kalau you ada pergerakan lagi banyak pelanggaran akan berlaku kan? So there'll be more collision, right? So there'll be more collision, and as a result, your mobility of the carriers reduce, okay, of both carriers. So that is the case at low doping level. So at that particular point, lattice scattering dominates. So on the other hand, if you dope your sample to higher level, heavily doped sample, effect of impurity scattering is more pronounced, but you dope, you include more and more impurity atoms into the lattice. Okay, then the mobility will be more dependent on the impurity concentration compared to the lattice effect. However, this impurity scattering introduced by the dopants will be more pronounced at low temperatures, where you don't have significant lattice vibration. Okay, at that particular point, kalau you dope heavily dope your silicon, then the impurity scattering will dominate, will determine the mobility of your carriers. The mobility increases as the temperature increases. The mobility increases as the temperature increases, as can be seen for a sample with doping of 1019. So if you go back to this, so you akan dapat kat sini ya, 1019. So what happens here at 1019? If you heat up the sample, if you increase the temperature to the right, you can see here, this case and this case, you akan dapat a little bit higher in mobility first before it drops. Okay, at this particular point, due to the increase in temperature, the mobility increases slightly. Okay, the curve is more dome shaped compared to this. This one is like negative gradient. Yeah, this one is like dome first, then goes down. Dome goes down. So these two cases are explained here. The mobility increases slightly as temperature increases, as can be seen with sample of 1019 and also 1018. 1018. However, if it's too high, then the mobility reduces again. Okay. For a given temperature, mobility decreases with increased impurity concentration because of enhanced impurity scattering. So for a given temperature, mobility decreases with increased impurity concentration because of enhanced impurity scattering. That means as you put more and more dopants into the lattice, so tendency untuk carrier to have scattering due to collision with impurities will be higher. So that's why at that particular point, the impurity scattering dominates the mobility of your carriers. Right? So is it okay so far? Just introduction to the mobility. I'm just going to stop here first, and we'll continue to recap on this curve tomorrow. Esok pukul 10 kan? 10 pagi. We're going to continue from here. Okay? So please make sure you understand first the effects of both doping and temperature, and which one dominates in which particular condition. Okay. Right? So I'll see you tomorrow then. I need to move to some other stuff now. Right? Okay then. Bye-bye. Thank you. Assalamualaikum. Stay safe. Selamat puasa. Esok dah Ramadan. Yes. Selamat puasa kepada semua. So after this, there will not be any more lunch question. Sampai raya. Okay, selamat puasa semua. Bye-bye. Thank you. Assalamualaikum.